In this video, we're going to talk about how to form a hemiacetal. And to form a hemiacetal, you're going to need a ketone or an aldehyde. Both will work. And you treat that with generally a weak nucleophile. So let's say ethanol. Treat that with a weak nucleophile. And these steps here are all reversible. And what's going to happen is you're going to generate a hemiacetal, which looks like this. You see that this oxygen atom right here is coming from that oxygen, and this alcohol right there is coming from that oxygen. When we do take a ketone or aldehyde, treat it with a weak nucleophile, this is generally a slow reaction. But you can speed that reaction up. You can make it go a whole lot faster if you add a catalyst. And the catalyst that you can add is an acid or a base. Both of those would work. Not at the same time. It's just an acid or a base. If you add that in, it will form the same product here. It's just at a much faster rate. And the reason why the acid-catalyzed reaction goes faster is because of the mechanism. And so I want to go through the mechanism to show you. I want to show all three. I want to show it with no catalyst, one with an acid, and one with the base. And I want us to compare and see why there is even a difference. So let's go through the mechanism here. And I highly doubt I'll be able to get all three on the board. So let's just start with the first one and see where we end up. All right. So let's take a look at our first mechanism here without any catalyst. And every step here is reversible. So electron-rich lone pairs, electron-poor carbonyl, like so, to generate this species. Make sure we have our lone pairs there. And now there's a third one, and then we have a O, H, and 2 carbons. And this oxygen has to be negatively charged, and this oxygen here would have to be positively charged. And that first step right there is called our nucleophilic addition step. Nucleophilic addition step. Okay, just abbreviate there. There's our nucleophilic addition step. And then we are going to have a proton transfer. And we're going to have a lot of ethanol because the ethanol is also the solvent. So we're going to have some ethanol here. And ethanol can behave as a base, and it not. And it can also behave as an acid. So what we're going to invoke is that this negative charge right here, electron-rich, is going to come in and grab that proton right there to do our proton transfer. And so that will generate our alcohol. But we still have that protonated oxygen right there that we need to take care of. And so we would do a second proton transfer, because what else did we generate? We generated some of this. Negatively charged species right there. And so that can do the other proton transfer, which would then come in, take electron-rich, grab that like so. Let's make sure we have that lone pair there. And then what's that going to generate? That will give us our there, just like that. And look at And then it would regenerate our ethanol, like so. Right. So we have nucleophilic addition, proton transfer. And that reaction right there goes very slowly. Now let's compare it when we add some base to it. Okay. So when we add base, what's going to happen is that the base, let's just say sodium hydroxide. Okay. We'll just do a generic base. We'll have some base there that's negatively charged. When you take that base and treat it with the ethanol, you're going to generate the alkoxide. Okay. And that is simply a proton transfer. So now what have we generated here? We've generated an electron-rich alkoxide. And so we can now take that alkoxide, okay, and treat it with our ketone now. Electron-rich, so that's going to come in and attack the carbonyl. Break that. So that's going to give us our product over here. So, oh, boom, boom. Negatively charged, like so. And then we have to do a proton transfer. Now when we add base to our ethanol here, we're adding a catalytic amount, just a little bit of base, not a lot. So most of the ethanol in the reaction is going to be ethanol. Only a small amount is going to be the ethoxide. So we have a lot of our ethanol still present. So we can do a proton transfer where we'll take that electron rich and do a proton transfer there to generate our product. OH. And there's our hemiacetal. So you can see that we get the same product. But what's different? It's the rate. So this one is very slow. Let's do it. Keep the color code here. This one's slow. And this reaction down here in orange is going to be fast. So I failed to type in here, what's this step right here? From this to that to here. That is a nucleophilic addition step. There's our nucleophilic addition step. So now, let's take a look here at why is the reaction on top without any base so much slower than when we add a base. Well, let's take a look here. In the green reaction here, we have neutral species. And then when we do the first reaction, look how many charged species we get. We got a negative and a positive. When you generate charges, that's going to be really high in energy. And so the energy of activation is going to be really high. And since that's really high, that reaction is going to go really, really slow. But in contrast here, what do we have? When we add the base, we have one negative charge. Okay? High in energy. But look at what happens when we do the first nucleophilic addition step. We only have one charge. So we went from negative or one charge to one charge. Whereas this guy went from no charges to two charges. And so that is way more higher in energy than when you just have no additional charges. And that's why there's a rate difference, is because at this nucleophilic addition step, right here, right, we don't generate additional charges. So what's happening here is when we add base, we are also generating a much stronger nucleophile than above. Because here, when we add base, we generate an alkoxide, which has a full-blown negative charge, which is a stronger nucleophile than when it's just neutral. And so if it's a stronger nucleophile, it's going to go faster. Now let's compare and let's contrast that, though, when we add base, or sorry, when we add acid. So what does acid do to make the reaction go faster? It's different, but it still gets the same net result. We're going to have a faster reaction than if we have no acid or base. So when we add our acid here, okay, let's just add a generic acid, HA, and that's treated with our alcohol here. What are we going to do? We are going to have a proton transfer, as you would expect, electron rich, electron poor. We're going to generate that species right there, plus our A minus, our conjugate base. So now we have a protonated alcohol. We are now going to take that protonated alcohol and treat it with our ketone here. But our ketone is going to now do another proton transfer. And it's going to take the lone pair there and snatch a proton. So that's going to generate a protonated ketone. So that's going to be positively charged. And we just generated some more ethanol right there. Okay. Now what's going to happen is we're going to now see that this carbon right here, this carbonyl carbon, is going to be more reactive than that carbonyl. That's what the acid is doing. It's making this carbonyl right here more electron rich when it's protonated compared to when it's not protonated. So because this carbonyl carbon is more electron rich than this one, we have a strong attraction, a stronger attraction for that guy to come in like so. Okay. And then when that does that, this bond's going to break, putting the electrons onto the oxygen. And so there is another reversible arrow. And what is that step called right there? That is our nucleophilic addition step. Right there. And so that's going to generate that species right there. And then we will have one more proton transfer. And what do we have a lot of that's just floating around? The ethanol. Remember, in this first step right here, not all of the ethanol is going to be protonated. We're just adding a small amount of catalytic acid. So we have plenty of ethanol still present that can now come in and act as a base to abstract that proton. And then that's going to generate our hemiacetal. But look what else it's going to generate. It's going to regenerate another protonated ethanol. And so we've regenerated our catalyst. So why does the acid catalyzed reaction form faster than no catalyst? Because we were making that carbonyl carbon more electron deficient. And so it's going to be more reactive. Now, you may be asking, well, why is that carbonyl carbon more electron deficient than this one? Well, because when it's protonated, it has that partial positive on that oxygen atom. And so it's going to want to take some of the electron density between the carbon and the oxygen and put more of it onto the oxygen to help stabilize that partial positive, or that positive charge on the oxygen, not partial, the positive charge. And so if more electron density is going towards the oxygen, then that's going to make that carbonyl carbon more electron deficient. Compared to this guy, this has more driving force to suck electron density towards the oxygen. Okay, so that is how you generate a hemiacetal.